Optimization problems, homework. This is going to be a video that shows how to do a few of these problems from a homework assignment on optimization. We're going to start with problem 2. Find non-negative numbers x and y whose sum is 75 and for which the value of x times y squared is as large as possible. So our equations that we're going to have to work with, essentially that we're given verbally, are x plus y equals 75. That's the sum of x and y. And over here we have our, say, total area, although it's not an area, I guess, more like a volume. We'll say is x times y squared. And we're going to work these two equations together to make one to maximize, and the one we want to maximize is this one on the right, because we want to make the product of x and y squared as large as possible. So we're going to take, we're going to reduce this equation on the left to a single variable by subtracting y from both sides of this equation. So we end up with x equals 75 minus y. And this 75 minus y, we're going to replace x with here. So we have t equals quantity 75 minus y times y squared. And distributing, we have t equals 75y squared minus y cubed. And now we're going to try to optimize this function by finding a maximum or minimum to the function. And we want to find the maximum. Let's go ahead and take the first derivative, which we will call t prime, equals 2 times 75 is 150. 2 minus 1 is 1, so y to the first power minus, I'll just put 1 there. No, I'll just even erase that. 1 minus 3y squared. And to find the absolute maximum, we need to find the critical numbers, and we'll set this equation equals 0. So 0 equals 150y minus 3y squared. We're going to try to solve this. We're going to divide this equation by 3, all sides, both sides, excuse me. So we have 0 equals 50y minus y squared, and factoring out what's our greatest common factor, y. So y times quantity 50 minus y is equal to 0. So our critical number is y equals 0 and y equals 50. So these are called our critical numbers. And to check this out, we're going to resort to a number line. And we have our critical numbers of 0 here and 50. And we're going to have t prime above this number line and the value of the maximizing function t below. And we're looking at non-negative numbers. So we're not even going to worry about this left of the critical number 0. But between 0 and 50, we're going to take this equation here, 0 equals 50y minus y squared. Pick a number between 0 and 50, let's say 10. Well, we'll have 50 times 10. Well, that's going to be 500 minus 10 squared. So 500 minus 100, that's going to be positive. And so between 0 and 50, the function value is increasing. And now to the right of 50, we'll pick 60, say. 50 times 60, well, that's going to be, I believe, 3,000 minus 50 squared, which should be I think, is it 2,500? 3,000 minus 2,500, that's going to be negative. So what we have is, we have, that's our maximum. So y equals 50, and that would leave x equaling, since their sum is 75, x equals 25. And those are our two non-negative numbers whose sum is 75, and for which the value of x times y squared is as large as possible. Okay, next we're going to go on to problem 4, which is kind of a classic perimeter type area maximizing problem. The farmer has 2,000 feet of fencing to enclose a pasture area. The field will be in the shape of a rectangle and will be placed against a river where there's no fencing needed. What is the largest area of field can be created, and what are its dimensions? So we will call one side of this rectangle W and the other side L. Of course, the river is another L, but we're not using that. So the perimeter, in this case, we have 2 times W plus L. And since we have 2,000 feet of fencing available, we'll say 2,000 equals 2W plus L. And the area is going to be length times width. So we can replace one of these variables here, either length or width, and I'm going to want to replace, I believe, length. So we say, if we solve for L in this perimeter equation, L equals 2,000 minus 2W. So our area here, replacing L, we're going to have 2,000 minus 2W times the width. And so distributing, we have area equals 2,000W minus 2W squared. And now we're going to take the derivative of area in order to maximize. So the derivative of 2,000W is going to be 2,000. And we're going to have minus 2 times 2 is 4W. And to maximize, we're going to find the horizontal tangent of this equation here, area equals length times width. And to do that, we're going to set the derivative equal to 0. So 0 equals 2,000 minus 4W. And we can divide this equation by 4 to simplify our arithmetic a little bit. So 0 equals 500 minus W. And solving, W is going to be equal to 500, meaning 500 feet. All right. And now we can go check using our number line. So we have 500 for W, and we have area prime and below area. And using this equation here, if we pick an area width of less than 500, we have 500, say 400, 500 minus 400, that's a positive. So area is increasing all the way to the width being 500. If we use a width greater than 500, say 600 feet, 500 minus 600, that's going to be negative. So 500 is our width. So width equals 500 feet. And length is going to be twice. We have 1,000 feet, right? So 500 plus 500, we have 1,000 left. So length equals 1,000 feet. And area is going to be equal to 500 times 1,000. So that's going to be 500,000 square feet, which I think is going to be well over 10 acres, maybe 11 acres. Pretty sizable little pasture area. Okay, we're going to go on to problem 6, which of this set I think is kind of the most challenging. And we have the size of the population of bacteria introduced to food grows according to the formula P of t equals 6,000 t over 60 plus t squared, where t is measured in weeks. Determine when the bacteria will meet its maximum size. What is the maximum size of the population? So, what I want to do for this one is we could use, since we're going to find the first derivative, we could use the quotient rule here. I would like to rewrite this equation in this manner. I'm going to write this as P of t equals 6,000 t, and instead of using the quotient rule, I'm going to multiply by 60 plus t squared, and since we've brought this 60 plus t squared out of the denominator, we're going to make this to the -1 power. So this is kind of a little trick to change a quotient rule problem into a product rule, which I think is usually easier for me to do. So we're going to say P prime of t is going to be the derivative of this first part, which derivative of 60,000 of 6,000 t will be 6,000 times the original itself, which is going to be 60 plus t squared to the -1 power, plus we're going to take the original 6,000 t times the derivative of this guy here, which is going to be times -1, and we have 60 plus t squared, and -1 minus 1 will be to the -2 power times the derivative of the inside, and derivative of 60 plus t squared is going to be 2t. And so, just kind of simplifying out a bit, P prime of t is equal to 6,000 over, we're going to take this to the -1 power, bring this back down below, 60 plus t squared, and we have minus, because this negative sign out front, see that, minus, we have 2 times 6,000, so we're going to have 12,000, and t times t is t squared, over, we're going to have this 60 plus t squared squared. So if we had used the quotient rule, we would end up the same place by now, but I think this is probably a little bit easier. Now, setting this equation equal to 0, we're going to have 0 equals, for maximization, equals 6,000. We'll just rewrite this, over 60 plus t squared and minus 12,000 t squared over quantity 60 plus t squared squared. All right, we're going to next try to clear out the denominator of this relation by multiplying everything by our largest denominator, which is going to be quantity 60 plus t squared squared. And when we do that, we're going to be left with 0 equals, well, we multiplied through this first term by 60 plus t squared squared, so we're going to get we're going to be left with 6,000 times 60 plus t squared. And then we're going to have a cancellation here of this here, 60 plus t squared divided by 60 plus t squared. We're going to end with 12,000 t squared. Next, we can divide this whole equation by 6,000. Okay, 6,000, 6,000. Okay, we're going to end up with 60. There are 60 plus 60 plus t squared. And we're going to have minus 12,000 divided by 6,000 is 2 t squared. And combining like terms, we have 0 equals 60 minus t squared. And solving, t squared is going to be equal to 60. So taking the square root of both sides, t is equal to plus or minus square root of 60. And square root of 60 we can write as square root of 4 times 15. And we can bring out this square root of 4, which is 2 times square root of 15. And we're interested in time being positive, right, within weeks. So we're not interested in the negative square root of 60. So time is going to be equal to 2 times square root of 15, which is our critical number. And now we're going to do a little number line analysis like we've done in the previous problems. So we go over here and 2 square root of 15. What is 2 times square root of 15? Well, I'll put pre-prime and p of t below. 2 times square root of 15 is a little bit less. Square root of 16 is 4. So 2 times square root of 15 is going to be a little less than 2 times 4, so a little less than 8. So I think it's going to be 7.7 or 7.8, something like that. So anyway, let's go ahead and take a number to the left, or smaller than 2 square root of, let's see, we're going to use this equation here. That's going to be the simplest form, 0 equals 60 minus t squared. If we use a number less than 2 square root of 15, we could use maybe 1. 60 minus 1 squared, that's going to be positive. Okay, and then a number greater than 2 square root of 15, we'll say maybe 10. Well, 60 minus 10 squared, that's going to be 60 minus 100, that's going to be negative. So we're going to have t equals 2 square root of 15 weeks. And then finally it asks, what is the maximum size of the population? Now, I'm going to leave a box in this answer. I do not have the calculator handy, but our p of our maximum is going to be p of 2 square root of 15, which is going to be equal to 6,000 times 2 square root of 15 over 60 plus 2 square root of 15 squared. So anyway, if we work all this out, we will get our maximum population. I'm just going to box this in as a uncalculated answer at this point. Anyway, I hope this has been helpful. Again, I think of these problems because of the differentiation. I think problem 6 is probably the most challenging one of this set. I hope this has been helpful to you, and thank you for viewing.